For decades, if you wanted a computer to recognize a cat, a programmer had to write strict step-by-step logic, calculate the distance between the ear points, measure the dimensions of the whiskers. But this code crashes the moment it encounters the messy reality of a tilted angle or bad lighting. Business markets and human behaviors present this same challenge. They are driven by thousands of shifting variables, like competitor budgets or consumer sentiment, that do not move in straight, predictable lines. Because we cannot write a rule for every possible real-world scenario, we need a system capable of looking at raw data and writing the rules for itself. This system is the artificial neural network. Inspired by a simplified model of the human brain, it processes information through layers of interconnected mathematical nodes, rather than following a rigid list of instructions. We can visualize this structure as a corporate hierarchy. The input layer acts as the frontline interns gathering raw data. The hidden layers are the middle managers who process and analyze that information, and the output layer is the CEO who renders the final verdict. In practice, this means hundreds of individual data points on the far left enter the network, where the information funnels through those dense middle layers until it exits as a single clear probability on the far right. But this architecture is just a skeleton. To understand why it's so effective, we have to watch it learn a task entirely from scratch. At the start of its life, a neural network is completely blind. Every one of its internal mathematical settings is randomized. Nodes rely on weights to prioritize incoming data, and a bias threshold to determine when to fire a signal. During feed-forward, raw data cascades through these randomized nodes to form an initial guess, which is almost always wildly incorrect. The network measures this failure using a loss function. It's a mathematical scorecard that calculates how many paces the model missed its target by. This specific measurement of failure provides the raw data the network needs to build intelligence. Intelligence begins with backpropagation. The network sends the error score in reverse, flowing backward to the input. Using an optimization routine called gradient descent, it systematically dials down weights that cause the error and amplifies connections pointing toward the correct answer. This cycle, guessing, measuring error, and adjusting connections, repeats millions of times across massive datasets. The network eventually carves a highly precise predictive model out of these millions of microscopic mathematical corrections. As the training loop repeats, the hidden layers in the middle of the network begin to organize themselves. They form a hierarchy of understanding. The first layer identifies simple lines. The second combines lines into shapes. The third assembles shapes into complex features, like a face. The machine discovers these concepts entirely on its own, without a human programmer. What we often call a black box is actually a self-assembling architecture of abstract definitions. When the training is complete, the loss function hits near zero, leaving behind a highly precise predictive engine. In manufacturing, this engine processes live assembly line video to detect microscopic cracks in machinery that human inspectors would likely miss. In finance, these networks evaluate hundreds of variables simultaneously, like transaction velocity and typing speed, to identify and block credit card fraud in milliseconds. This shifts the human role from writing the step-by-step logic to defining the destination. We provide the data and the objective, and the network organizes the internal pathways required to find the solution.